Okay, one of the things I don't really have to spend any time on is that we're not that interested in carbon neutrality compared to carbon dioxide removal now. So carbon dioxide removal has more or less been accepted. So I will skip the first few slides on why carbon dioxide removal is a good thing. And but I'll mention this one. This is from a European report a few years ago, looking at the different options for carbon dioxide removal. And they're all options that you're familiar with, forestry management, agriculture management, et cetera, et cetera. And these are the 6 topics that were covered in the European report. But there was one very obvious approach that was overlooked in that report. It's been overlooked for a long time, and that is the safe burial of agricultural biomass, which we call agro-sequestration. And we looked up to see who's the first one who brought this up, and it's someone who's extremely famous, Freeman Dyson, who's one of the most creative physicists of the 20th century. And he already proposed this in 1976. He wrote the paper on this. So this is quite remarkable. I think this is before people were worrying that much about CO2. They were just starting to think about it. And his idea was to bury wood. And I'll come to that and how good an idea that was. But it is very similar to what I'm going to be describing. Now, nowadays, carbon dioxide removal, there's an X Prize. So in the middle of an X Prize competition, $50 million to the first prize, the best way to pull CO2 out of the air. And why is it hard? Because we're starting with a very low concentration of CO2 in the atmosphere. And then when we convert it to biomass, like wood, the carbon is at full density inside wood. And so this great increase in concentration ratio has an entropy associated with it. And kT log of the concentration ratio is 17 kT, is about half a volt. And where does the energy come from to concentrate the CO2 in the biomass? It comes from photosynthesis. The plants provide the free energy in the course of doing photosynthesis. So it's a good thing to keep in mind that it's kind of like solar energy. I will rely very heavily on biofuel project, which was a very big project about 15 years ago. And many of the things we need, like the optimal plant species, et cetera, the productivity and the cost and the place, the space, all of that was worked out by the biofuel people. And they pointed out that in producing cellulose, cellulose is not food. It's much easier for the farmer to grow, because if you grow food, the insects are competing for the food, and it's much harder to grow. And you don't need insecticide, and the yield is also much higher when you're just producing cellulose. It could be 3 times higher yield. This is all worked out by the biofuel people. Now, I was strongly influenced in my own development. People ask me, how do I get into this? I got into this when I got into solar cells. And that was already over 40 years ago. And it was at Exxon, which was a petroleum company, but at that time they were the world's biggest manufacturer of solar panels. And we had as one of our consultants this gentleman from RCA, which was a very famous electronics company in those days that developed radio, developed television, developed color television, and also in the US at least introduced advertising to broadcasting. So then made even more money from the advertising. But he was my mentor, and one day he asked me, you passed some gasoline stations on the way to work. Please tell me how many dollars per megajoule of gasoline. And likewise, you can look up the cost of maize. In Chicago, they buy and sell maize, and you can figure out what is the cost of maize per megajoule of maize. So maize is a carbohydrate, it burns, and it has megajoules. So what is the dollar cost? And he told me, figure it out and let me know. And I figured it out, and I was shocked that the cost of gasoline and the cost of maize per megajoule is almost the same. And in fact, he was teasing me because he already knew the answer, because he had already published it. In this paper, he points out that how efficient agriculture can be. And ever since then, I have been very highly respectful toward agriculture. And what the plan is then, not to make biofuel, but to dry the biomass and put it in an underground environmental chamber. And you'll see why it has to be dry, and that it is lined with very thick polyethylene to keep it dry. Let's go on to that. So I published this paper in April, and if you can spell my name, you can look it up. And Ekman's name is a little bit easier, and you can find it online. You can Google it. Now, what is the first thing that is wrong with biofuel? Why am I talking about sequestration instead of biofuel? And here's the main reason. If you grow plant matter, the approximate formula of the cellulose is CH2O. That means the carbon is already half oxidized. And so if you want to make a biofuel, it takes 2 acres or 2 hectares of agriculture to make 1 hectare of biofuel, because the biomass is half oxidized. On the other hand, if you simply bury the biomass, you take the entire carbon out of the atmosphere. So it's one of the many problems of biofuel. But nonetheless, we rely very much upon biofuel for many of the numbers needed for this discussion. Now, what is the problem with simply burying it? This is what was suggested by Freeman Dyson, is that even if you bury it anaerobically, there are microbes, fungi, and even insects that can survive under anaerobic conditions. So it doesn't help to make it anaerobic. And so how do you solve the problem of the decomposition of the biomass? In fact, the cellulose, for example, in trees, it chemically likes to decompose into CO2 and methane, which is very bad. And if you think about wood, wood is about 70% cellulose, which decomposes right away, and about 30% lignin. Lignin forms the beautiful grain of the wood, and is a very durable chemical, and is the problem. One of the problems in biofuel is they can't process lignin because the molecule is too stable. So if you simply bury the wood, it's still good for something because the lignin is preserved. So you have 30% preservation or 30% sequestration. It's better than nothing, but we'd like to have 100% sequestration. So now we get into the scientific part. How do we guarantee 100% sequestration? I have to get into dryness. So dryness is really the point of the talk. And that is, if it's a dry day, we say the relative humidity is low. Okay. Now, but that applies to the atmosphere. What if you had a solid material? So I have here a picture of a steak, and let's say we dry the meat, and the meat will be more preserved when it's dry. And so, well, how dry does it have to be? We have a word. We don't use the word relative humidity for solid materials. We have the corresponding word for solid materials is water activity. The concept of water activity is the same as the concept of relative humidity, except for solid materials. And so you ask, how dry does the meat have to be in order to prevent, for example, decomposition or attack by microbes? And so this has been investigated. It's a very important question. And at 60% water activity, which is equivalent to 60% relative humidity, all metabolism comes to a stop, and the food is safe to store. So who has investigated this is in the United States, the Food and Drug Administration. And let's say you have some food and the inspector says, how dry is it? What's the water activity? You say the water activity is 40%. The inspector will say it's safe, wrap it up in cellophane and put it on the supermarket shelf. So below 60% water activity, metabolism stops. And in fact, this has also been investigated by NASA because they're interested in life on other planets. How much water does life need? So bacteria need 95% water activity. Yeasts need 85%, mildews 80%, et cetera, et cetera. By the time that you get to 60% water activity, all metabolism stops. And this is supposed to have stops. I've added this word. And it's safe. It's safe. It's stored. It does not decompose. And in fact, this is not anything new. This is an example of what the Native Americans did in the Pacific Northwest of the United States. It was very easy to catch salmon. They would put the pieces of salmon out in the sun to dry, and they could preserve it for a long time. So, in a way, this is known since very early days. Now, you say, well, how much water is there if you get 60% water activity? So this is a graph of the water activity is on the horizontal axis. The vertical axis is the weight percent water. And so at 60% water activity, you have less than about 12% water by weight. So it gives you an idea, and it's somewhat similar for miscanthus and grasses, and even for hardwoods are somewhat similar. Down around 12%. It's dry enough so that the biomass does not decompose. So our goal is to then to grow the biomass materials, the same as the biofuel people, but we dry the biomass. We have to artificially dry it, or we could dry it in the sun, but usually the farmers are impatient. So they dry it with heat. You put the dry biomass into an underground chamber, which is sealed with the 4 millimeters of polyethylene. And how big does this chamber have to be? Well, if you have a 1 hectare sized chamber, it will sequester 10,000 hectares of agriculture. So only 1/10,000th of the land area is used for the environmental sequestration chamber. But it doesn't mean the agricultural land is lost, because then you cover it over with more dirt and it turns back into farmland again. And so this gives you an idea. Then there's a problem, though. Even with 4 millimeters of polyethylene will allow some diffusion. About 2 microns equivalent liquid water diffuses through that thickness of polyethylene every year. But the thickness of the biomass is it can be, for example, 30 meters. And then 2 microns per year means that the biomass will last for thousands of years. So that's the whole secret of the talk. Dry the biomass. Don't simply bury it in the ground, dry it. And then it will last for thousands of years. Now, I'll skip this except to say, yes, we need to sequester 20 gigatons. And where's the land going to come from? This was also investigated by the biofuel people. There are various reports, but I can show you on this slide in a nice bar chart. The width of this bar is all the land on Earth, and some of it is ice at the North Pole and the South Pole. Some of it is on mountains, and we can't use it. Some of it is in cities. This little part is in cities. A lot of it is used for agriculture, for forestry, for shrubs. Let's look at the agricultural part. Oops, let's go back one. The agricultural part consists of pasture for grazing animals and row crops. So the row crops will be like rice and wheat and so forth. So if you just take a little bit out of the pasture, this is the amount of land area to remove 20 gigatons of carbon dioxide from the atmosphere every year. And so it's a relatively small amount. It has already been identified in those government reports. So that's where we do the agriculture. The cost of the agriculture is, there are different ways of calculating it. We've done it bottoms up, added up all the components of cost. But another way is to see what is the farmer paid when he sells his crop, and this is all published by different governments for their own agriculture, and approximately $500 per acre. Pardon me, this is approximately 0.4 hectares. to convert it to a metric unit. So that would be like $1,200 per acre is what the farmer receives, and so the agriculture the farmer needs to make a profit. So the cost of the agriculture is less than $500 an acre, or $1,200 a hectare. And so that gives you a cost limit. And you also know the yield because every country publishes the yield. First, let's talk about the cost. The agricultural cost is very well understood. It's been studied and is published in various regions. And then we have to build the environmental chamber. The environmental chamber has the same construction as a landfill for garbage, except for garbage, we have to prevent it from contaminating the groundwater. We are doing the opposite. We have to prevent the dry biomass from being contaminated by water. So we need to keep the water out. But not all of the respects is known, and the cost is known because there are contractors who build these landfills. So it works out to be roughly $30 for the agriculture, $30 for the environmental chamber, $60 total per ton. And I think you all recognize this is a very low cost in comparison to other methods of sequestration. How severe is the problem? Well, we need to sequester 20 gigatons of CO2, and we know the price. I just worked it out. It's $60 a ton, and you multiply it out, and it ends up that it's a large industry. It's $1.2 trillion. But sounds big, but it has to be measured against the world economy, which is $100 trillion. So it's 1.2% of the world economy over the next 50 to 100 years. So it's not a disaster. It's something that you can tolerate, you can live with. Now, so we sent the paper off for publication, and the referee came back and said, paper looks all right, but you need to find an example where nature has preserved biomass for thousands of years. You have to find an example from nature. We found an example, but it was not exactly from nature. Let me show you what it was. It was a very famous mountain in Israel, and it has a flat top. So in California, we call that a mesa. It has vertical walls, so it's very easy to defend. It was the last holdout against the Roman legions. So it's a tourist attraction. But part of it is a palace, or if you prefer, a castle that was built by King Herod. So like other kings, he was afraid of being overthrown. So he built a castle in a very easily defended place because the walls were almost vertical. And the castle was built there, but it's in a very dry location. It's adjacent to the Dead Sea. And the top of the mesa is at sea level. The bottom of the mesa is approximately 400 meters below sea level. So it's a very, very dry place. And it's hard to get to. So it wasn't disturbed for thousands of years. And actually, an archaeologist that I'm going to excavate. And so this guy is a very famous archaeologist because he excavated the palace of King Herod. So here I have a picture of, or a carving of King Herod. Here's the Israeli archaeologist. He excavates in 1965. He puts all the architectural relics away and is stored, and he himself only lives to the 1980s. And but one of the things he discovered in the palace, he discovered these seeds. These are seeds for the date palm tree. And so a medical doctor in Jerusalem hears about this, and she requests these seeds, which were kept in a drawer since 1965. And she sends the seeds out to be carbon dated. And the date comes back that the seeds are 2,000 years old. Then she gives the seeds over to this lady. She's a horticulturalist, and she plants the seed and gets a small plant and eventually transplants to a bigger pot. And indeed, this is a date palm tree. And figure 5 of my paper is a photograph of this date palm tree. It's of historical significance and cultural significance. So they put a fence around it to protect it. So you see the fence. This tree is germinated in it's in 2005 from a 2,000-year-old seed, and now it's 2023, and the tree is 18 years old. And it shows if you keep things very dry, they can be preserved for 2,000 years, like these particular seeds. Having a little trouble. Oh, here it is. It's working now. Yeah, I'm having trouble forwarding my slides. Let me switch to a different mode.
Probably hit escape, maybe, Eli.
Yeah, I can do that, but I'm reluctant to do that. Okay, and now it's working. Okay, so let me hide the controls again. Okay, so I have a few slides to talk about agriculture. I'm almost out of time. Everything that I've told you, all the numbers, were based upon current agricultural practices, but agriculture keeps improving. In the least developed countries, the agricultural productivity grew by 2 times over a 50-year period. And in electrical engineering, we call this Moore's Law. And here's some similar data from Great Britain. This is the best data I found. It goes back to the 1700s. I plotted only from 1800, but it shows that the agricultural productivity grew by a factor 2 in the 1800s. Then in the 2000s, the agricultural productivity grew by 4, largely because of the invention of the Haber process for making artificial fertilizer. And this is some similar data. It shows in the past 50 years, the amount of land needed has for agriculture has fallen. And in fact, the United States, vast areas of farms have been converted to woodlots. Over 50 years, the world is using 68% less land to produce the same amount of food. So this gives you some perspective. So let me summarize. How do we solve the climate crisis? We need to be scalable, so agriculture is very scalable. We need a low cost. The $60 a ton corresponds to 53 cents a gallon. My apology for the American units, but the cost represents 1.2% of the world GNP, so it's something, it's not a catastrophe, it's something can be managed. We have proven sequestration over 2,000 years using dryness. That's my whole talk, is dryness. There are many schemes that are very clever, but we will need to maybe wait hundreds of years to see if there's no bad side effects or whether they work. So it's very predictable. So we need predictability. Sometimes it's overlooked, and we can implement it rapidly because farmers change the crops every growing season. And so we could start this type of sequestration in April, just a few months away. So I have to apologize. I'm a high-tech guy offering a low-tech solution. And we can't take a risk for how things will turn out hundreds of years from now. So I'm arguing that it has to be low-tech and it has to be proven. And this agro-sequestration, from the example I gave you, has 2,000 years of proof. So the rest of it is just a statement. We still need to do everything. We need conservation. We need alternative energy. We need carbonization, decarbonization. We need other forms of sequestration. There are many other forms of sequestration. We need an all of the above approach, in spite of the fact that I've argued very strongly that this is at least puts an upper limit on how much this is going to cost. Okay, so I've gone a little bit over, but let me ask for questions. Oh, I have one more slide to show, 2 more. We started a company to do this. We're recruiting at all levels for this company. And so if you have students, you can tell them to send me a CV. But then we understood another company is doing exactly the same thing. They read our preprint, they like it, and they're coming to a similar cost as $100 a ton. That's slightly different. This company has a CEO, a CTO, a CFO. It's getting going, and it has $14 million from Bill Gates. So we now find ourselves competing with Bill Gates to do exactly what I'm describing. So let me quit on that and wish us luck. Thank you.
Thank you so much, Eli. Thanks for giving us a chance to have a look at the whole process, and now we can actually dive into details during the discussion. So I encourage the audience to put questions in the Q&A box. I see there's already a couple, and we can get started with a question from Harry Edgewater for you, Eli. Harry says, one of the learning elements from biofuels cultivation is the cost and the CO2 footprint of feedstock transportation to the biorefinery. So the question is, does your analysis take into account the transportation cost and CO2 footprint that you need to spend in order to collect and bring the biomass into the point of burial?
So, Harry, it's great to meet you this way. And I gave the similar talk at Caltech when you weren't there. So you're absolutely right. The transportation cost is extremely important. And that's why we sequester in the environmental chamber is built under the farmland, right in the farmland. So the distance of transportation is very short. We try to restrict it to a 5-mile radius, or let's say an 8-kilometer radius, to keep the cost of transportation very low. And we don't do any processing. There's no biorefinery. There's a slight processing. We have to dry the crop, but every farmer has to dry his crop. And have we taken this into account? Yes. The way we look at it is in terms of carbon efficiency. So if you sequester 100 tons of carbon dioxide, how much carbon dioxide did you have to use in order to do the agriculture and the shipping and the transportation and so forth? So we've gone through this very carefully, and because these crops are very efficient, it works out that for 100 tons of sequestration, the farm equipment and everything generates 5 tons of emissions. So we have about 95% carbon efficiency. So it is very important to do that. But that's a very good question. Thank you.
Following up on that, Eli, so essentially one thing that is potentially quite intriguing of this approach is that you are growing the biomass potentially at the point of burial, right? You don't need, in principle, you can grow these plants and then bury them right there. Is that
within
one of
a few kilometers? Yes.
Mm-hmm. Yeah. So I guess then the question is, what is the amount of energy and resources that you need in order to grow these plants? So you would not have transportation costs, but you would have the cost of growing the plants.
Well, we have a small transportation cost. We also have the cost of the fertilizer. It has both a financial cost and a CO2 cost. And so that's all included. And that's what the 5 tons of CO2 emission to sequester 100 tons of CO2. That's similar to the previous question in that regard. And this information is available in our supplementary information. So we have a paper that's like 6 pages, but then we have 85 pages of supplementary information that's available at the Proceedings of the National Academy of Sciences paper. So you can get the supplementary information where we provide these details. And thank you very much for the question.
Great, thank you, Eli. So a couple more questions in the Q&A box. So Emily is asking if there is any concern about the carbon dioxide permeability of polyethylene. And she's asking whether this was considered when the material thickness was determined.
Yes, we're not worried because we're not storing carbon dioxide, we're storing biomass. And the problem we have is not diffusivity of carbon dioxide. The problem we have is diffusivity of water. And polyethylene has very low diffusivity of water. And that's one of the reasons we chose it. And I can tell you the amount is that 2 microns of liquid water are diffusing through the polyethylene every year, but the environmental chamber will be 30 meters thick, and so the dryness of the plants themselves will give us thousands of years of safe sequestration.
I guess maybe interpreting a little bit the question and rephrasing it. I know you said that the metabolism then will stop eventually with an appropriate drying level and water activity. So it means that there's no gases that are produced eventually within the polyethylene compartment if that's done correctly, right? So there's no CO2 or methane being produced.
Yes, and this has been validated in research labs, Food and Drug Administration, NASA, and so forth. And they use the most sensitive analytical instruments, gas chromatography, and so forth, to validate that there would be no generation or no decomposition. But when we do this, the first few examples of these environmental chambers, we're going to have it fully instrumented with all the proper instruments. We'll have PhDs inspecting it and validating it. But this is drawn from the prior work on food safety and also the prior work on how much water might be needed to find life on other planets.
And there's a question from Ali, and the question is if there is any possibility that the polyethylene could be damaged when filled with dry biomass.
So I'm not worried about the biomass damaging the polyethylene. What I'm worried about is, for example, we cover the polyethylene with dirt so it becomes farmland again. What if a tree grows up and it sends one root deep down and damages the environmental chamber? Likewise, what happens if an animal digs down there and causes a hole in the polyethylene? So it's not the end of the world if that happens, because it doesn't decompose right away. It will take decades to decompose if something bad happens, and it's not one environmental chamber for the whole world. It's let's say one environmental chamber in an acre. And so if something bad happens, it shouldn't happen, but if it's bad, it can be corrected. But there's another way of looking at it, and that is that if we have it deep enough, the animals will not go beyond a certain depth. The tree roots will not go beyond a certain depth. We budgeted 20 meters of depth. What if we need 21 meters or 22 meters? At some point, we will be safe. And according to our calculations, the cost increases by 40 cents per meter of depth. So if we need an extra, let's say, 5 meters, then the cost will go up from $60 a ton to $62 a ton. So it's simply a cost question.
Great. Harry adds another question. Both Harry and I yesterday were at the local conference here at around Stanford, discussing about CO2 capture technologies, and MRV, measurement, reporting, and verification, is becoming a very important topic of discussion for pretty much any technology that one can consider nowadays in this field. So Harry is asking, the MRV and carbon credits depend on the permanency of storage. So it is true that you're saying that this seed was planted 2,000 years ago, and there's actually a carbon dating for burned forests that show us that some of the biochar can last for many thousands of years. But do you have any further data to demonstrate how long the polyethylene moisture barrier will last?
Well, there has been a tremendous amount of work on how much moisture diffuses through that thickness of polyethylene. And by the way, 4 millimeters is very different from a polyethylene shopping bag. It's It's a very tough, strong material. So it's high density polyethylene. We did the plants were not planted 2,000 years ago. They were just found in this castle and shown to have been there for 2,000 years. They were only planted in 2005, 18 years ago, and the tree is 18 years old. So I would say that we are extremely reliable in terms of longevity, to the point that I think after the first few examples of these are built, then people will be willing to accept that this is nothing bad will happen over that long period of time. And so in that respect, simply monitoring is not enough, because what if something bad happens? What if there's a side effect 200 years from now? So I think we need some form of certainty and safety going into the future. So I agree with that, but I would say the monitoring just tells you something went wrong. We don't want something to go wrong, and so we need society needs some degree of certainty, but definitely the first few examples will be monitored just to be safe.
Certainly. So need more experiments to be done for sure for MRV. One question from me, I wonder if I missed during your talk. Clearly, you have ideas on specific plants that can be used for this, and you showed there's quite a bit of knowledge accumulated because of the biofuel area. But is it possible to potentially use this approach for discarded biomass that would be, coming from other types of plants?
Yes, our approach is completely agnostic with regard to the source of the biomass. It just has to be dry. And so I didn't talk about using discarded biomass because I wanted to show that we could scale to solve the worldwide problem. But for certainly, people are going to use discarded biomass, but it'll be a partial solution. But they could make a good profit doing that.
Mm-hmm. It's a little bit of a crazy idea, and I actually don't think it will work, but I wanted to ask, is there any possibility of using vacuum rather than drying, that you could, in principle, have a pretty good barrier that would preserve vacuum for a certain amount of time? Let's imagine we have a technique that would allow us to ensure that we can evacuate that polyethylene compartment for 10,000 years. Would that be an opportunity to consider, or is vacuum not an option?
I don't think it would change anything, because what happens in the environmental chamber, it's anaerobic. So the oxygen is, what little oxygen is present is immediately eaten up. And even if you had vacuum, you would still be concerned about water diffusivity. So we believe the important question is the water diffusivity, which has been very carefully measured for these types of polyethylene.
Perfect. Thank you, Eli. Are there any other questions from the audience that we haven't addressed? Maybe I'll ask a couple more questions then, Eli, if I may. One is, you showed a very useful graph of the area that we use on the planet for agriculture, and the fact that in principle, we certainly could use only a fraction of the agricultural land in order to perform carbon capture. There's still clearly a competition with food, and I was discussing with colleagues last week. There was some data showing in some parts of Indonesia how locals had to dry some of the wetlands over there that act as a carbon sink in order to grow crops for food. So when we think about local or people that need to decide between food and carbon capture, they will certainly decide to grow food. So is there any chance to avoid competition with food? And it's also the question about the discarded biomass. So
I showed you the historical record that there's a Moore's law for agriculture. And the Moore's law is the agricultural productivity doubles every 50 years. And will it continue? Yes, we have CRISPR, we have other modern things. There will be continued improvements in agriculture. But let's look at today's situation. The United States is the world's largest producer of maize by far. 40% of American maize is going into gasohol, which is not even carbon neutral. Okay, when you talk about 40% of maize, of American maize, you're talking of 40% of the state of Iowa. The state of Iowa is a huge state, and it's already, all that land is available. Let's talk about something that happened to me last week. A farmer called me up from Alabama, and he said he has loblolly pine, and he wants to use it for sequestration. And I said, why aren't you doing normal agriculture? And he said that 15 years ago, the US government came to all the farmers in the southeastern United States. This is a huge region going from Arkansas, which is west of the Mississippi River, all the way to Georgia. And the government said, look, you cannot compete with the rich farmland in the Midwest. You're just going to drive prices down. Instead of just paying you not to farm, why don't you convert to woodlots? So he told me that this problem existed in all of those states. There are vast areas of loblolly pine, which is mature and needs to be harvested. So there might be some competition, but the world historical trend is actually going in the opposite direction. Malthus was wrong. One of the reasons he was wrong is that the agricultural productivity doubles every 50 years. And whatever problems there are in Indonesian agriculture, excess population or growth and so on and so forth, it's very clear that there is a tremendous amount of underutilized farmland worldwide. And it's a worldwide problem. We need a worldwide solution. There are plenty of places where we can grow biomass without competing with food. And people have had this problem for 200 years. They felt that there was not enough farmland. But this is coming from Europe, where there isn't that much land anyway. It turned out Malthus was wrong, largely because of the improvements in agricultural productivity.
Okay, thank you. Then maybe last question from my side. If there was anything that you would be able to ask policymakers, what would that be? What would be your request?
Well, that's a very, what I would request is that there should not be a carbon tax. Instead, there should be a carbon mandate. And the mandate would be as follows. If you put 1 kilogram of carbon dioxide into the air, you need to take 1 kilogram out of the air. And this would be much more effective than a tax because every coal company and every petroleum company would have to pay not a tax, but they would have to pay to pull the carbon dioxide out of the air. And this is better than a tax because a tax never goes away and gets used for other purposes. But if you have a mandate, it can only be used to pull carbon dioxide out of the air. And so you have a source of financing, and you're guaranteed that the money will go for the desired purpose to save the climate.